The definition of the derivative will give us a way to figure out the slope of the graph of a function at one single point. Let's see how. Remember the definition of the derivative. This is it. It says the derivative of f prime of a is equal to the limit as t approaches a of this difference quotient, f of t minus f of a over t minus a. To see how that's going to help us get the slope at one point on the graph of a function, let's start with a picture. Here I've drawn the graph of a function. I'm not going to tell you the formula for this function. I'll just tell you the function values as we need them. I've picked a particular point a here. The point I picked was a equals a half, and the corresponding function value is 1. And I'd like to try to figure out what the slope of the graph of the function is at this one point. That is, what's its slope? How fast is it going up right at that one point? But unfortunately, all I have is one point, and there's lots of lines I could draw through one point. There's many lines I could draw. Neither of these lines seem to match the graph of the slope of the graph of the function. I really want a line like this to match the slope of the graph at that one point. But I don't know how to pick that exactly. I can only guess at it. I can only eyeball it. And calculus provides a more exact way of doing it than just guessing at what that line might be. Instead of using one point, which doesn't determine a line, I use 2 points. So I'm going to choose another point over here, t equals 3. And when t equals 3, the corresponding value of the function turns out to be 1.7. Now I have 2 points. 2 points are better than 1 point because 2 points determine a line uniquely, determines this blue line, and I can calculate the slope of this line. And the slope turns out to be equal to exactly this difference quotient here. That's why we're using the difference quotient. It's equal to the slope of this line. And if I put in these values into this formula, I find out that this slope is 0.282. That's the exact slope of this line right here. It's not the slope that I want because t is way too far away from a. So I need to move t closer. In this picture, I've moved t a little bit closer. I've moved it to 2.5. And I've again drawn this line through the green and the red dots. And when t is equal to 2.5, I can compute the slope just like I did over here, and the answer turns out to be 0.365. Well, that's a little bit better, but it's way too far away still. So I want to continue this process of moving t closer and closer to a and see what happens. The process is important. So when t is equal to a little bit closer, here I've gotten t a little bit closer, I get another line and I can figure out its slope. When t is equal to 2.25, I've gotten closer. The slope is 0.409, dot, dot, dot. And then I can move t a little bit closer still, and I get another dot. When t equals 2, I get another line. And when t equals 2, I get a slope of 0.456, dot, dot, dot. And I want to continue this process of moving t down the axis towards a, tracking this red dot, and tracking these corresponding slopes. So I'm moving t down the axis towards a, and as that process happens, I want to track the corresponding slopes. So to see what that looks like, let's draw another picture. Here's t equals 2 again, and I'm thinking of this motion process to take this limit. So the limit as t approaches a, I put t in motion, and so I'm moving t closer and closer to a. So I move t a little bit closer, I get a new slope. I move t a little bit closer, I get a new slope. I move t a little bit closer, I get a new slope. I move t closer still, I get a new slope. And I continue that process in the limit. And in the limit, as t moves closer and closer to a, it's gotten very close to a now. And then in the limit, I get the slope of one particular line. And the slope of that line is the derivative. And it gives me the slope, f prime of a, at that one single point. So by using the theory of limits, I can get the slope of exactly 1 point. That's the derivative. This is the definition of the derivative. It's the basis for all the other rules and theory about derivative that follows.